Welcome, focused learners, to today's explainer. I am so incredibly excited to guide you through this material because we are going to look at one of the absolute most fascinating intellectual journeys in human history. Our goal today is to give you a step-by-step guide, really a student's roadmap, tracing the evolution of physics. We are going to travel all the way from Galileo's simple wooden ramps in 17th century Italy, right up to the modern, super complex computer algorithms that model real-world flight today. It's an incredible story of how human ingenuity mapped the physical world. Let's get into it.
It really begs the question, doesn't it? I mean, how exactly did we go from a guy rolling bronze balls down a piece of wood to calculating the precise atmospheric drag on a spacecraft entering orbit? It seems like a massive, impossible leap. But, as we'll see, it's actually just a sequence of incredibly clever, logical steps. Mastering these basics is absolutely essential if you want to understand anything about modern engineering, aviation, or just how our physical world truly works. Okay, let's dive into this and bridge that gap between 1604 and modern computational physics. Here is our roadmap for today. 1. The inclined plane method. 2. Music and time measurement. 3. Independence of forces. 4. Ideal motion versus reality. 5. Air resistance influence. And 6. The real flight algorithm.
Starting off with Section 1, the inclined plane method, the genesis of kinematics.
So let's step back in time to the year 1604. Galileo Galilei wants to understand gravity, right? He wants to know how things fall. But there's a massive problem. If you just drop a heavy stone, it falls so rapidly that measuring its descent is basically impossible, especially with the primitive tools they had back then. He needed a way to, well, slow down the action. His solution was absolute genius in its simplicity, the inclined plane. By placing a highly polished bronze ball on a smooth wooden ramp, he essentially diluted the force of gravity. Instead of an instant, totally unmeasurable vertical drop, the ball experienced a manageable, uniform acceleration down the ramp. He was analyzing the downward pull of gravity by observing a slowed-down, angled version of it. It's like he invented the slow motion button.
Moving right along to Section 2, Music and Time Measurement, Finding Rhythm in Physics.
Now, solving the speed problem created an entirely new one. Think about it. Even if the ball is moving slower, how on earth do you accurately time a rolling object without a modern stopwatch? Clocks back then couldn't measure anything shorter than a second. Well, the answer, amazingly, lies in music. Galileo was actually an accomplished lute player, and it is objectively wild to think that a fundamental pillar of modern physics was cracked simply because a guy playing a lute had a really good ear for rhythm. Historians believe he set up adjustable gut frets along his wooden ramp. As the rolling ball hit these frets, it made a little audible bump. By relying on his finely tuned internal musical rhythm, he adjusted the frets until the bumps occurred at perfectly equal time intervals, just like maintaining an even beat in a song. He didn't need to know how many actual seconds passed, he just needed equal ratios of time.
And this brilliantly illustrates his monumental discovery. By measuring the increasingly large distances between those frets over equal beats of time, he figured out that the distance the ball traveled was proportional to the square of the time. This linear change of velocity over time is the very definition of uniformly accelerated motion. Think of a car smoothly speeding up on a highway, gaining the exact same amount of speed every single second. That is uniformly accelerated motion in a nutshell. It's this elegant, perfect mathematical relationship that was quite literally birthed from musical beats.
All right, Section 3, Independence of Forces, the Rule of Vectors. So, now that Galileo understood uniform acceleration, he needed to understand how objects moved freely through the air. This brings us to a foundational concept in dynamics, the independence of forces. The absolutely crucial point here is that horizontal and vertical forces act completely independently of one another. If you throw a stone forward, the horizontal velocity pushing it outward has absolutely zero effect on the vertical gravity pulling it down. Because of this rule, if you were to drop a ball straight down from a cliff and throw another ball perfectly horizontally off that exact same cliff at the exact same time, they will both hit the ground at the exact same moment. The downward acceleration is identical, regardless of the horizontal motion. Mind-blowing, right?
Let's look at Section 4, Ideal Motion versus Reality, Breaking the Mathematical Illusion.
With tools like uniform acceleration and independent force vectors, we can calculate a beautiful, perfect parabolic curve for any thrown object. But we are now leaving the comfort of Galileo's theoretical vacuum. It's time to enter the messy, chaotic, real world. You see, in a textbook vacuum, kinematics are perfectly predictable. You get symmetrical parabolas and constant, unchanging downward acceleration. But in reality, we have an atmosphere. Air friction, or drag, completely ruins the perfect math. Drag pushes back against the object, meaning the acceleration isn't just gravity anymore. It's changing constantly depending on how fast the object is moving through the air.
Now, what's really interesting about this slide is that stark visual difference between theory and reality. Look at the dotted line there. That is our mathematically ideal parabola without any air resistance. Now look at the solid line. That squashed asymmetrical curve is the actual trajectory of a real projectile, like a baseball, once air resistance is accounted for. It travels significantly less distance and doesn't go nearly as high.
Which brings us to Section 5, Air Resistance Influence, Deconstructing the Drag.
So what exactly is causing this massive squashing effect on our trajectory? Let's deconstruct the elements of this drag force. It isn't just one simple number. It actually relies on several factors. First, the density of the air itself. Second, the silhouette area, basically how big the object looks from the front. Third, and this is a big one, the shape of the object, which gives us a specific drag coefficient. This is exactly why a smooth golf ball, a stitched baseball, and a feather all behave wildly differently in the air. And it's why the sports industry spends millions of dollars optimizing the exact drag coefficient of their equipment. Finally, drag is proportional to the square of the velocity, meaning the faster you go, the exponentially harder the air pushes back.
And finally, Section 6, Real Flight Algorithm, the loop that solved physics.
Because drag force depends on velocity, and velocity is constantly changing as the object flies, the acceleration is also constantly changing. You can't just plug this into one simple algebra equation anymore. To figure out where the ball lands, we have to use numerical methods. We need computers. This is how modern machines solve the very friction problem Galileo originally identified. It's called numerical integration, and here is the step-by-step algorithm. Step 1. You calculate the acceleration at one exact instant, accounting for the drag force. Step 2. You use that acceleration to update the object's velocity for just a tiny fraction of a second. Step 3. You use that new velocity to update the object's physical position. And Step 4. You advance the clock by that tiny fraction of a second and loop right back to Step 1. By repeating this cycle thousands of times a second, laptops can map the exact, messy trajectory of literally any real-world object.
Think about how far we've come. We started with a wooden ramp and musical beats just to find uniform acceleration. We then broke forces into independent vectors. And finally, we used simple repeating computer loops to conquer the messy reality of atmospheric drag. But I want to leave you with this provocative thought. If this basic four-step loop can calculate a baseball's trajectory, how do you think these exact same fundamental physics principles are scaled up right now, at this very second, to calculate the atmospheric re-entry of a massive SpaceX rocket? The mechanics of motion scale endlessly, and this journey from the loot to the laptop is really just the beginning. Thanks so much for diving into this explainer with me today, and as always, stay curious.